We'll now continue our discussion of section 6.4, talking about the graphs of trigonometric functions. We're going to look at one additional example where we are graphing a transformed trigonometric function. So our example asks us to sketch the graph of f of x is equal to negative 2 secant of pi x plus pi over 2. So on the screen we have a picture of our secant graph. So this is the graph of f of x is equal to secant x. And if you recall, when we began this section, we talked about how to draw that secant graph. We know that the period of the secant graph is 2 pi, and you can see that in the picture. You can see that we have a complete down opening parabola here. We have the right half of the parabola opening up here, and the left half of it opening up over here. And so that distance from 0 to 2 pi is going to represent our period. Now, we also talked about how it might be easier to have complete parabolas instead of having a situation where we have it broken up into two different places. So with that in mind, I'm going to extend this one more tick mark. This would be 5 pi over 2. It would also have an asymptote because remember that our asymptotes are occurring at every other marked off value here, or at the odd multiples of pi over 2. And we're going to extend that graph up to make the other part of that parabola. So now I'm specifically going to look on this graph at the portion of the graph that is between pi over 2 and 5 pi over 2. Now, it doesn't change the period, it just changes the portion of the graph that we're looking at. So what I want to do is give you kind of a general definition for a function that has been transformed, and then we're going to come back to this example. All right, so this definition says that if we have a trig function that's set up this way, f of x is equal to a sine bx minus c, or it could be a cosine bx minus c, then the amplitude is going to be denoted by the absolute value of a. So remember that the amplitude is the height of the graph, and so we can get the amplitude of the graph by looking at the number that sits in front of the function. The period can be determined by 2 pi over b. And we've actually already seen this formula and worked on it in a previous example. So we know that that's true. 2 pi over b is going to give me the period. Remember, if there's a number sitting in front of the x, it always impacts the period of the graph. All right, and we have a phase shift that can be calculated by doing c over b. And in our last presentation, we looked at an example that had a phase shift. So we know that that is impacted by this c value. What is added or subtracted onto the problem here is going to produce a phase shift. So just keep that in mind as we move forward with this example. So as I look at this example, let's talk just a second about amplitude. All right, so if I'm looking at the number sitting in front of my function, I can see that the amplitude is going to be 2, because remember that the amplitude is the absolute value of the a. Our a value is negative 2, and the absolute value of negative 2 would be 2. So we know that the amplitude is going to be 2, which essentially means that instead of this graph bottoming out at 1 right here, it's going to bottom out at 2. It's going to shift it up. And instead of us having a negative 1 value right here at the top of this parabola, that value is going to move down to negative 2. So we'll keep that in mind as we draw our graph in just a minute. Okay, we also see that we have a pi value here in front of the x, and so that is going to impact my period. That's your b value right here. Remember that to calculate your period, you're going to do 2 pi over b. So for us, that's going to be 2 pi over pi. So our period is going to be 2. So no longer will our period run from 0 to 2 pi, or from pi over 2 to 5 pi over 2 on this graph, but the period's going to run a distance of 2. Now, the question becomes, how are we going to start and end a particular cycle of the period? For example, here we're starting at pi over 2 and we're ending at 5 pi over 2. When we adjust for the period, what are our starting points and our ending points? So the easiest way to do this is to take the part of your function that is inside the parentheses. So this part is the period change and also the phase shift. To take that and set it equal to the starting and ending points of your original graph. So in other words, we're going to take pi x plus pi over 2, and we're going to set it equal to pi over 2. Because on my original graph, that is where I'm starting the original graph. So let's calculate this. We're going to solve this for x. So I'm going to subtract pi over 2 from both sides. So that's going to give me pi x is equal to 0. And then we're going to divide both sides by pi. And so that's going to give me x is equal to 0. So on my original graph, I started at pi over 2. On my new graph, I'm going to start it at 0. Okay, let's do the ending point. So again, I'm going to take my function, pi x plus pi over 2, and I'm going to set it equal to the ending point on my original graph. And I'm going to solve for x. So I'm going to subtract pi over 2 from both sides. This is going to give me pi x is equal to 5 minus 1 would be 4 pi over 2. So simplifying that fraction, we'll get 2 pi. And then I'm going to divide both sides by pi. Again, solving for x. And so we get x is equal to 2. So again, our original function, one period, ended at 5 pi over 2. Now that we've transformed it, it's going to end at 2. So we now have a starting point and an ending point. We know that the period is 2, which makes perfect sense because we're looking at starting and ending from 0 to 2. That is a period of 2. And we know that the amplitude is 2. I'm just going to write down my information here. So we're going to start at 0 and end at 2. Okay, so let's see if there's anything else that we need to know before we draw our graph. So we've taken care of the period. We've basically taken care of the phase shift in that we've shifted to a starting and an ending point that represents this problem. We know what the original graph looks like. We know that the 2 is going to change the amplitude. What does this negative do out in the front? So remember that if you put the negative in front of a function, it's going to reflect that function over the x-axis. So that's the last thing that I need to keep in mind, that it's going to reflect over the x-axis. Okay, so let's try to just real roughly sketch this out, and then we're going to look at the graph that the book gives, which will be a little bit more finished. All right, so I'm going to go ahead and draw a graph. I'm going to put my starting point at 0 and my ending point at 2. Okay, remember that you started with an asymptote and you ended with an asymptote, so we will still have that same pattern going here where we start with an asymptote and we end with an asymptote. Okay, we know that the graph is going to come in and hit at 2 and at -2. All right, so we have an asymptote at the beginning and asymptote at the end. Note you also have an asymptote in the middle. So I'm going to go ahead and put that one at 1. That would be our middle point. So now my only question becomes, and you may or may not really have this question, but as I'm doing this, I kind of wonder sometimes if I need to do an up opening parabola here or a down opening parabola here, and sometimes that is a bit confusing for students. So if you find yourself confused at that point, it may be a good idea to pick a point and just do a quick table of values, and really all you need is 1 point. I'm going to go ahead and pick something in this first set, this first interval from 0 to 1. I'm going to pick a half. All right, and then all you would need to do would be to go to your original function and plug in a half. So if I do that, I'm going to have -2 secant. I'm putting a 1/2 in for this x, so I'm going to have 1/2 pi plus pi over 2. So basically I have pi over 2 plus pi over 2. Half and a half make a whole, so this is just going to equal pi. We know that secant at pi would be the same thing as well, it would be the reciprocal of cosine at pi, and cosine at pi is going to be -1, so secant would also be -1 at pi. And we see that that value is equal to 2. And so what that tells me is that at 1/2, 2, I have a point. And so that helps me narrow down how this graph is going to look as I get started. So I've got a parabola here that opens up. I have a parabola here that opens down. And then I could continue drawing as many cycles of this graph as I wanted. And we can check it, like I said, against what the book has. Here's the graph that the book has, and this is exactly what we just drew. We just drew the portion from 0 to 2. So if you look simply at this part, it should match up exactly to what we just drew.